Welcome to an introduction to electrical and computer engineering. My name is Lee Brinton. I'm an electrical engineering instructor at Salt Lake Community College. In this video, we'll be talking about ways to analyze circuits using the node voltage method. We're going to start by looking at the similarities between elevation and voltage. We'll then discuss the difference between branch voltages and node voltages. We'll introduce the concept of nodes and critical or extraordinary nodes. We'll then look at the actual process of analyzing circuits using node voltages, and we'll look at how that applies when there are dependent sources and supernodes present in the circuits. First of all, the similarities between elevation. If we want to talk about the elevation of, say, Mount Olympus, we've got to define, first of all, what we're measuring relative to. In other words, we establish our reference. Typically, sea level is our reference at 0 feet. Mount Olympus, then, is about 9,500 feet above sea level, and the Salt Lake Valley floor is around 4,100 feet above sea level. On the other hand, if we're standing on the valley floor and looking up to the mountains to the east, we'll see that the elevation, the amount that they rise, can be calculated by taking the higher elevation, 9,500 feet, less the lower elevation of 4,100 feet, and we've got a 5,400 foot change in elevation going from the valley floor to the top of Mount Olympus. On the other hand, if instead of calling sea level our reference, we made the valley floor our reference, and said then that the elevation here equaled 0 feet, then Mount Olympus would be 5,400 feet, and sea level would be negative 4,100 feet. Elevations are all relative to a reference. And similarly, that's true with voltages. To understand that, let's make sure we understand the concept or the difference between a branch voltage and a node voltage. A branch voltage is the voltage across a branch within the circuit. In this case here, we've got a 3-volt drop across this resistor. Over here, we've got a 10-volt drop across that resistor, similarly a 2-volt and a 12-volt drop across those resistors. On the other hand, if we wanted to talk about the voltage at a point in the circuit, we would need to specify what we were referring it to. So let's create, or call this node here 0 volts. And then, as we come along this branch, we go up from 0, up 15 volts. So at this point, the voltage there is 15 volts above 0, or above our reference. Now, as we traverse this branch here, we drop 3 volts, getting to a voltage here of 15 minus 3 is 12 volts above our reference. Continuing on along here, we drop another 10 volts to 2 volts above our reference, and then continuing on down across these 2 volts back to our 0 reference. Thus the distinction. A node voltage, or the voltage at a node, is a voltage at the node relative to some reference, whereas the voltage across the branch is just the drop across the single element within the branch. Up until now, as we've been analyzing circuits, we've identified branch currents and voltages and worked with those as our variables. For example, we have a branch current here, call it I1. We have another branch current here, call it I2, another here, I3, I4, and perhaps referencing it like that, I5, and of course we know that I5 in this case equals I0. But in order to analyze this circuit using branch currents, we would have 5 different variables. And when using those variables, we could then write KVL and KCL equations and solve for any branch voltage or branch current in that circuit we wanted to do. The node voltage method involves, rather than branch currents, it involves our defining node voltages. In order to do that, we need to specify or to make the distinction between nodes and extraordinary nodes. A node is a point where 2 or more branches are joined. Here we've got a node. There's another node here, there's another node there, and here's a node, and then all the way along the bottom here is yet another node. So we have 1, 2, 3, 4. When I said that was made a mistake there. This is all one node. 5 nodes. So 1, 2, 3, 4, 5 regular nodes. And now we have this node here where we have more than 2. We have 3 or more branches coming to these. Those types of nodes are referred to as extraordinary nodes or critical nodes. In other words, a node is a place where 2 or more branches come together. An extraordinary or critical node is a place where 3 or more branches come together. In this case, we have 1, 2, 3 extraordinary or critical nodes. Our approach is going to be then to identify the critical nodes, choose one of them as our reference, and define variables at the other 2 nodes. And then with those voltages, write Kirchhoff current law or KCL equations at each of those critical nodes in terms of V1 and V2. For example, let's start by summing the currents leaving this node right here. In terms of V1 and this, our voltage source, we can note that, first of all, note that the voltage at that node is V0 volts above our reference. Now we can write an expression for the current leaving this node by taking the voltage at this side minus the voltage at this side of those resistors and dividing by the resistance. In other words, we're specifying the branch voltage across those 2 resistors in terms of our node voltages, or thus we would write V1 minus V0 divided by R2 plus R3 would be the current leaving our first node going to the left. Now let's do similarly for the other 2 branches and sum those 3 currents together and acknowledge that the sum of the 3 currents leaving that node must equal 0, just Kirchhoff's current law. So the current now leaving that node coming down through R1 would be V1, the voltage at the top, minus the voltage at this side, which in this case is just 0, divided by R1. And finally, the current leaving node 1 going to the right would be the voltage at the left-hand side of that resistor would be V1. The voltage at the right-hand side would be V2. So V1 minus V2 divided by R4 represent the sum of the 3 currents leaving that node, and the sum of those 3 things must equal 0. Similarly, we write another KCL at node 2. So this is node 1. And then at node 2, we have the current leaving node 2 going this way is going to be the voltage at the right-hand side, V2, minus the voltage at the left-hand side, V1, divided by R4. Note right now that the voltage or the current leaving node 2 going to the left is equal but of opposite sign to the current leaving node 1 and going to the right. And you'll notice those 2 terms are the same in each of these equations other than they differ by a sign. This term in the first equation, V1 minus V2 over R4, and that term in the second equation, V2 minus V1 over R4. All right, continuing on, we now add the current leaving V2, or leaving node 2 going down. That voltage will be, or that current rather, will be V2 divided by R5, plus the current leaving the node going in this direction. Well, actually the current is going in, so we'll subtract minus I0 equals 0. The sum of those 3 currents equals 0. So here we have 2 equations with 2 unknowns. It becomes simply a matter of algebra at this point to solve for those 2 currents, or for those 2 node voltages.